Hello students, let us have a look at our fifth chapter, that is Electromagnetic Waves. After studying this chapter, you will be able to explain the displacement current, discuss the electromagnetic waves and their characteristics, define the Maxwell's equation, understand the transverse waves, explain the electromagnetic spectrum. We will first try to understand what is electromagnetic waves. Electromagnetic waves are a phenomenon of nature first observed as light. The electromagnetic radiation actually exists in an infinite spectrum. The electromagnetic radiation itself is created by causing a charged particle such as the negatively charged electron or positively charged proton that makes up the atoms of our body or the furniture on which we are sitting to be accelerated. Together, the electron and proton form a neutral atom. When the electron and proton are separated, we can then observe the electron's negative charge and proton's positive charge. It is when these separated charges are accelerated that create that electromagnetic radiation. The electromagnetic spectrum includes from longest wavelength to shortest, radio waves, microwaves, infrared, optical, ultraviolet, X-rays and gamma rays. Displacement current. The idea of displacement current originated from the study of the discharge of a capacitor. Maxwell asserted that since all electric currents are closed in the discharge of capacitor, the conduction current is closed by a current known as displacement current arising due to charge in electric displacement in the dielectric flowing in the dielectric between the capacitor plates. Maxwell showed that it was necessary to assume that a current of the same value also flowed in the dielectric gap. For a given charge density sigma on the capacitor plates, the electric field in the dielectric gap is given by E is equal to sigma divided by epsilon, where epsilon is the permittivity of the dielectric. From this, sigma is equal to epsilon E is equal to D, where D is the electric displacement. Electromagnetic waves and properties. Electromagnetic waves are propagated by oscillating electric and magnetic fields oscillating at right angles to each other. Electromagnetic waves travel with a constant velocity of 3 into 108 ms-1 in vacuum. Electromagnetic waves are not deflected by electric or magnetic field. Electromagnetic waves can show interference or diffraction. Electromagnetic waves are transverse waves. Electromagnetic waves may be polarized. Electromagnetic waves need no medium of propagation. The energy received from the sun is received by the earth through electromagnetic waves. The wavelength and the frequency of electromagnetic wave is related as geometric optics is a simplification of the wave optics which assumes that the wavelength is much smaller than the geometric dimensions of the optical system. Geometric optics is a valuable tool for the treatment of light propagation, light rays, reflection and refraction. Incident ray of light strikes an object and reflects when it strikes a boundary. Normal line is a perpendicular line of boundary and angle of incidence is an angle between incident ray and the normal. Angle of reflection is an angle between the reflected ray and the normal. Maxwell's equation. Maxwell's 4 equations describe the electric and magnetic fields arising from varying distribution of electric charges and currents and how those fields change in time. It was made evident for the first time that varying electric and magnetic fields could feed off each other. These fields could propagate indefinitely through space far from the varying charges and currents where they originated. Gauss's law for electric fields. The integral of the outgoing electric field over an area enclosing a volume equals the total charge inside in appropriate units. The corresponding formula for magnetic fields: no magnetic charge exists, no monopoles. Faraday's law of magnetic induction. The first term is integrated round a closed line, usually a wire, and gives the total voltage change around the circuit, which is generated by a varying magnetic field threading through the circuit. Ampere's law plus Maxwell's displacement current. This gives the total magnetic force around a circuit in terms of the current through the circuit plus any varying electric field through the circuit, that's the displacement current. Transverse waves. In a transverse wave, the medium has particles that vibrate in a direction perpendicular to the direction of the propagation of wave. Here, the formation of crest and trough takes place. The polarization of transverse wave is possible. These waves can propagate through solids and liquids, but not through gases, because gases do not possess elastic properties. A transverse wave is a moving wave that consists of oscillations occurring perpendicular or right-angled to the direction of energy transfer. If a transverse wave is moving in the positive x direction, its oscillations are in up and down directions that lie in the YZ plane. Electromagnetic spectrum. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum of an object has a different meaning and is instead the characteristic distribution of electromagnetic radiation emitted or absorbed by that particular object. Radio waves generally are utilized by antennas of appropriate size with wavelength ranging from hundreds of meters to about 1 millimeter. The super high frequency SHF and extremely high frequency EHF of microwaves come after radio waves. Microwaves are waves that are typically short enough to employ tubular metal waveguides of reasonable diameter. The infrared part of the electromagnetic spectrum covers the range from roughly 300 GHz 1 mm to 400 THz 750 nm. Visible light is the part of the EM spectrum to which the human eye is the most sensitive. Visible light and near-infrared light is typically absorbed and emitted by electrons in molecules and atoms that move from one energy level to another. UV in the very shortest range, next to X-rays, is capable even of ionizing atoms. See photoelectric effect, greatly changing their physical behavior. After UV come X-rays, which, like the upper ranges of UV, are also ionizing. However, due to their higher energies, X-rays can also interact with matter by means of the Compton effect. Hard X-rays have shorter wavelengths than soft X-rays. Gamma rays are the most energetic photons, having no defined lower limit to their wavelength. They are useful to astronomers in the study of high energy objects or regions, although this must be done by orbiting gamma ray telescopes orbiting outside the Earth's atmosphere.